Everyone, and first of all, let me thank the organizers to come once again this year to this beautiful place. So this year I decided to split the lectures in two independent parts that will focus on two types of devices that want to investigate two different effects. The devices are made to be as simple as possible to study the two effects I will mention. So the first one is a Josephson junction. That will be used to probe topological superconductivity in mercury telluride. And the second device drawn here, which is the one I will focus on today, is a capacitor, a plate capacitor made of a gold top gate and a topological insulator. And I will try to show you how we can probe screening effects and electrostatics in mercury telluride topological insulators. So as I just said, the lectures will be two independent ones. So today I will cover this part, which focuses on a very old paper from I think 1980 something by Volkov and Pankratov, where they first introduced something which is now understood as topological surface states. And I will try to show you that beyond these topological superstates that most of you know already, there are some additional states which we named simply volkov-pankratov states, which are somehow excited surface states and that can play a role in some interfaces or some heterojunctions. And I will try to show you how we've probed this directly in the experiment. So first, I will not follow history so much, and I will first do the theory and then come to our experiments. You should know that both have been done independently, and this is just a matter of coincidence that we came to talk to each other and that we've realized that maybe there's some connection between the two works. So this theory and experimental parts are mostly explained in much more detail than what I will do today in those three papers. This is a work that I've been doing in Paris, where I now work, together with my former group, the University of Würzburg. And there's also a big chunk of theory that has been done together with some theorists from Lyon, from the group of David Carpentier, and from Orsay, especially from the group of Marc Gerbig. So first of all, let me try to introduce mercury telluride and what is known as mercury telluride as a 3D topological insulator. As Claudia mentioned this morning, the topological character comes in mercury telluride from the fact that there's an inverted band structure, meaning that the p-type orbital here is above the s-type orbital, and there's an inversion gap of about 300 millieV. While in most semiconductors, such as cadmium telluride, for example, this is the opposite. And you simply understand that when you will create an interface between these two materials, you have to connect bands with the same symmetry, and you will necessarily have a band crossing, which will host some surface state. You should, however, be careful that in mercury telluride, the Fermi level is actually here between the two subbands, the gamma-8 subbands, so that in principle, mercury telluride in itself is not really an insulator, but rather a semi-metal. So what is done in mercury telluride to really see the topological character is to strain the mercury telluride. Just simply during the growth, you grow it on some cadmium telluride substrate, and there's a small lattice mismatch that will strain the mercury telluride lattice. And this will lift the degeneracy and open a small gap. So you here have the recipe to form a 3D topological insulator from mercury telluride, where you have to be careful here that there's a small transport gap, which is the one that you will see in transport experiments. But the inversion, the topological character, comes from this band inversion here between these two bands, which has a lot larger energy scale. These materials, I will not enter into details, but these materials are MBE grown. They have a very, very high mobility on the order of 3 to 5, 10 to the 5, and very low residual doping, which is quite an ideal situation to study topological physics. And indeed, already quite some time ago, in mercury telluride, were identified quantum Hall plateaus. As you ramp up the magnetic field, you start to see in the conductance, in the transverse resistance, you start to see quantum Hall plateaus, which are the hallmark of the 2D surface states that are lying at the top and the bottom surface of the topological insulator. Now what's interesting is that if you look carefully at this sequence here, you have only an even sequence of, an odd sequence of Hall plateaus here, namely I equals 1, 3, and 5. And this is characteristic of the two Dirac cones of the top and bottom surfaces, which for this particular gate voltage have the same density. So if you tune the density on the top and bottom surface to be equal, then you have two surface states with the same density and you recover two Dirac cones. But if you don't do that, then if you don't tune the density properly, then you will have two Dirac cones which may behave differently because they have different densities, so they will have a different response to the magnetic field. But you can track the whole response and, for example, look at the maxima of this derivative, and this will tell you where the transition from one plateau to the next quantum Hall plateau takes place. And you can identify this maxima here as the dotted, as the circles here. And you can see that they come from two fans here, and those two fans are the two surfaces, or the top and bottom surfaces. And for example, you can see that these two subsets of Landau levels have different broadening because, for example, the top interface is a lot dirtier because it's directly connected to some insulator. It's terminated during growth, and then you do some lithography on top of it. So it's usually a lot rougher and a lot dirtier. So you see this directly in the broadening of the Shubnikov-de Haas oscillations, and you can also see at look at the gate influence and see that one gate has the gate has a larger action on one subset of the Landau levels, and this is just because the top gate acts more strongly on the top surface than on the bottom one. And this is basically what you would expect to see in an ideal topological insulator, to have nice surface states that show the quantum Hall effect when you turn on the magnetic field. But there's something strange to that. The first thing is that actually, as previously shown, you see those quantum Hall plateaus for a very large range of gate voltage. And from the gate voltage, you can sort of estimate by how much the charge is changed between one gate voltage and the other. And you actually see that this corresponds to a huge amount of charge, which is not compatible with the fact that there should be also some bulk states. And that at some point you should heat the bulk states and start to fill the bulk states. So there's something which is not clear here. And this has been reported in this work from Würzburg. And they started to think that maybe the surface state, since they are at the surface, will screen the electric field that you try to apply with the top gate, and will influence the way the charge can be transferred from the surface states to the bulk to an ohmic contact or something. So that when you try to change the density in your surface states, you may or may not change the density in the bulk itself. And this is interesting in itself because it may show some intrinsic response of the surface states, which is peculiar to the topological states. But this is also important to understand this effect when you try to manipulate, for example, heavily doped material that you try to gate to something like a Dirac point. And this is what triggered this work, and I will try to show you how we investigated this screening of the surface states and how we've come up to some ideas that I hope will trigger additional work on the topic of screening. So first, I want to introduce a basic toy model that we've been working on. This is a very basic toy model. This is as simple as one can do it. It is not compatible with Poisson self-consistent equations, so you should understand it as a toy model. But it has for us the main ingredient to understand in more detail. It adds some more richness to the topic of topological interojunctions, and I will try to show you in which sense. Just to say that because of this non-compatibility with the Poisson equations and so on, I don't know myself how much of this is compatible with, for example, what Joel will show in the next lecture. This is still open for discussion, and I'm happy to discuss this. So our main idea is to start with the following statement. When you try to look at a junction between two insulators, one of them being topological, then you are in the typical situation where you have an insulator with a negative band gap, which would be here mercury telluride with a 300 millieV inversion gap. And on the other side, you have a trivial insulator, which would be, for example, cadmium telluride. And you say that since the gap has to change sign because you try to match these two wave functions and these two, then at some point you will have a crossing of the gap and a closing of the gap, and you will have this direct point. And in most works, this interface is taken to be as small as possible and infinitely short. But one has to remember that there's a natural length scale to that problem, and this length scale is, for example, the one you can construct using VF, the Fermi velocity, and something which is homogeneous to an energy, so something like the gap. In fact, in our work, what comes out is this combination, delta 2 minus delta 1. And this is the natural scale that you can construct in a topological heterojunction. And our idea was to suggest that indeed, even if the interface is infinitely sharp on the atomic size when you connect the two interfaces by the MBE growth, for example, there will be a mechanism, something like charge reorganization, that will introduce this natural length scale and will force the system to have a gradual change. And this may be surprising, but if you think about what's happening in a superconductor, if you look at the proximity effect between a superconductor and a metal, you have this coherence length over which the electrons or the Cooper pairs in the superconductor will penetrate into the normal metal. And this is known as the proximity effect, and this has been studied for 40 years. In the same way, there's something similar in the semiconductor. When you form a p-n junction, there's always a typical length scale, which is the same h bar VF over delta. And this is the screening length. This is connected to screening in semiconductors and so on and so forth. So this is our starting point. Now, the theorists have tried to look at this model, and they've done it in the simplest way they could, which is to take the gap to change linearly with position over this length psi that I've just introduced. And if you look carefully at this model, in this 4-band minimal Hamiltonian, you see that after some unitary transformation, it really looks like the Dirac Hamiltonian in a magnetic field. So this is just a purely formal analogy between this Hamiltonian, where there's this Z varying parameter, and the Hamiltonian of graphene, for example, in a magnetic field. And to see this analogy, you need to write this as ladder operators of this form. The formulas here are not important, so don't bother too much. And the electric field, and there's a characteristic magnetic field or electric field. If you write it, just convert one to the other with a velocity, which is this one. And again, you have a typical critical field, which is analogous to the Zener field in semiconductors, which is given by this change in the energy gap divided by the size of the interface. And what does it change in the spectrum? Well, you now see that for interfaces of finite thickness, then you do not only have these topological surface states here, but you have a family of states which are nothing but the Landau levels that you find from this artificial magnetic field. And you can see different things. First, you can In this simple toy model, you can write this analytically and see that they behave just like graphene Landau levels of that form. And you see again that the magnetic field here is given by this critical field that I just introduced. You can also see that the M equals 0 state is a bit special. That's the topological one. It's non-degenerate, while the other ones are doubly degenerate. Now you can ask yourself, what's the, is this of topological nature? What's the nature of these excited states? And in some way they are not topological because they are doubly degenerate. They are not protected against backscattering in the same way as the topological surface states are. But they are topological in the sense that they only appear in the conditions that you have this delta 1, delta 2 being negative, this product, which means that either delta 1 or delta 2 is positive, which means they don't have the same size, the same sign, which means that you have a topological interface. And in that sense, they only occur at topological interfaces or topological heterojunctions. Now, another thing that has to be remembered here is that in most cases, you just don't care about two states. Because this length here is quite small, usually, on the order of a few nanometers. The energy scales that are associated to these Landau levels is quite high, which means that they will be very high in energy, and mostly in most cases in transport, you will just not feel them. So why would I bother introducing them? Well, I told you that I want to focus on the screening, on the screening of the surface states, and I will just show you that these states that I will now on call the volkov-pankratov state have a very strange response to the electric field. Now, why do we call them volkov-pankratov states? Because if you look at this very old paper from Volkov and Pankratov, they did not only predict the topological surface states, but also a family of excited states. And no one, as far as I know, no one really realized the connection that there could be between these states and topology. So now how do these states behave when you add an electric field? Now that you want to change the density in your topological insulator, you want to act with your top gate and change the density and try to probe the transport over a wide range of electron density. Well, you can do this again analytically. Here, I've pointed out the analogy between the formal analogy between this Hamiltonian, the Hamiltonian that describes this interface, and the one of graphene in a magnetic field. Now you try to add an electric field to the problem. It's like having a crossed magnetic and electric field, and again in graphene this can be solved analytically. And one gets the following problem. First, you look at relativistic states in crossed electric and magnetic field. So you can do something which is like a Lorentz boost with a factor, with a beta factor, which is now the electric field that you try to apply with the top gate, divided by this critical electric field that I introduced previously. And you find the following. You find that at zero energy, you have these volkov-pankratov states at rather high energy. Here is the topological surface state. Here you have these volkov-pankratov excited states, and here you have something which is meant to represent the bulk bands, for example. But as you increase the electric field, you will move along this line or along that side. It's the same thing. But you will see the following. First, what happens is that you will have a general softening of the Fermi velocity, which means that the whole cone structure which you have will have a change, will experience a change in the Fermi velocity, which will now look like this. So the Fermi velocity will be smaller, and equivalently the Dirac cone will be a lot flatter. I think I didn't check the references, but I think a few theory works have pointed out this response. But now what is strange is that One can also see that the volkov-pankratov states will have a strange response to the electric field, and they will actually try to go down towards zero energy. And they will do this in this manner with this exponent. It doesn't really matter. But what's important is that they will go down to zero energy, and they will, of course, be more prominently probed in transport. This means that as you will drive your gate voltage to change the density, you will also change the electric field. You will also modify the wave functions of this volkov-pankratov state, and you will modify their energies so that they come down to zero energy. So this means several things. This means that now you have found solutions of this problem which correspond to zero electric field in the bulk, which means that these surface states now completely screen the electric field, which means whatever you do with your top gate, you will only act on the surface states for a large amount of electric field until you start to reach this volkov-pankratov states, and then this screening will start to break down. And I will show you in the experiments that we may have signatures of that. So this is in some way this anomalous screening, this Dirac screening that had been pointed out earlier. The other thing is that the energy scales, or the electric field scales that are relevant to that problem are actually quite huge. They are on the order of 500 Tesla. So you may think this is totally not realistic in our experiment, but if you actually put the numbers for that electric field, this is more or less the maximum electric field we could reach in the experiment using a very, very thin insulator. So this will become more and more, this will become clearer in the next slide. Okay, so let me know if you have questions now, because this is more or less what I wanted to point out, that there are these volkov-pankratov states which can play a role in screening, and especially at increasing electric field, and that they will prevent charge to be transferred as easily as you would imagine between the gate and the bulk, because they will screen the electric field. Yeah?
Could you please come back to the natural length and explain what is that?
That's, okay. That's a very early slide. Oops, I went too fast. This is just, if you take dimensional analysis, you see that you can construct a natural length scale, which is psi given by h bar Vf over some energy.
What was it represent?
This is the natural scales that appears, for example, when you look at screening in semiconductors or coherence lengths in superconductors. This is just for now purely dimensional analysis. But what I want to point out is that it has to appear somewhere in the problem. When you look at junctions, they will naturally, there should be a natural scale over which the transition happens. And this natural scale is given by this scale. And in principle, you could have interfaces that are atomically sharp on the crystallographic side, but it's very likely, though we cannot really explain in detail the mechanism yet, it is very likely that the charge will reorganize. As in a semiconductor, you should remember that you deal with topological semiconductors in some way. The charge will reorganize so that the interface will in the end be on the order of this natural length scale. And of course, if you do a different type of interface, you could imagine that the interface is even shallower than that. Yes.
But those in another space. I mean.
Well, this is the K space. Yeah, this is the local band structure on that side. This is the local band structure on the other side.
Yeah, but those delta are in K space, and this
yes.
is in real space.
Yes. But you just assume you have a local band structure that will evolve locally, and this is where I think. Joel was this morning pointed out that in some sense this could break down, and that one should be careful about this. So this is something that I wanted to discuss with him.
The next question was
Yeah.
Why do you use graphene as a model?
I don't use graphene. I just pointed out that if you take the minimal model of this direct cone here, a 4-band minimal model, you could actually see that formally this is equivalent to looking at graphene in a magnetic field. And you can use this, what is known about graphene, to solve analytically this problem. This is just a form of analogy. There's no need to involve graphene in any other way.
Because graphene has generated states, and those are not...
Yeah, this is formally like graphene, but there's no other connection to graphene. You should only remember, you should only consider that this can be solved analytically. You don't even need to involve graphene. It's just the way the theorist found the way to treat that.
And then by using this model, you kind of saying that you're generating an effective magnetic field, right?
Yes. Okay, so now I'll try to show you how we try to probe this in the experiment. And for this, I want to introduce the devices I've shown on the very first slide, which is metal oxide topological insulator capacitors, where one gate here is used to induce a DC electric field, so to change the density, for example. And also now that we've understood to induce a given electric field, now you should understand that the electric field and the density are independent variables. But also to induce an AC signal that will be used to measure the capacitance of this stack here. You create a plate capacitor between the gate and the topological insulator. Now you can change different things. You can change the frequency at which you excite this gate. You can change the electric field, which is equivalent to changing the voltage on this gate. You can change the chemical potential or the electron density plus the temperature. And what you will look at is the capacitance of this stack, and I will show you in which way this is relevant and interesting. And I will show you that we can also access the conductivity of this layer, or equivalency at the resistivity. So what do you measure in such a capacitor? Well, you all know the plate-plate capacitor, where there's a geometric contribution that tells you that when you want to transfer charge from one plate to the other, there's an energy cost associated to that, which is for a charge E squared over C, where C, the geometric capacitance, just given by epsilon times the area divided by the distance between the plates. Now, if you look at a device in which one of the plate has a finite density of state, there will be an additional energy cost, which only takes into account the fact that if you want to add an electron, you need to go across the electric field, but you also need to pay an additional energy to increase slightly the Fermi level. In a metal, you don't care because there are many, many available states, but in a semiconductor, for example, the density of state is low and you need to pay some energy. And this energy is directly given by the density of state, and you can actually show that this is equivalent to writing an additional energy cost, which is E squared over C, where C is the capacitance, and the quantum capacitance directly proportional to the density of state. And since you have to pay both energy costs, you have to add the energy cost, which is equivalent to adding the inverse capacitance, which means that you now have two capacitance in series. Okay? Is it clear? Yeah? This is true. This is true as long as there are no fancy interactions, issues, and so on. This is just to say that there's a special energy cost in the semiconductor due to the finite density of state. This is the same way you can treat, for example, Coulomb interaction in quantum dots. You can formally see sometimes that there are capacitance all over the places. These are these quantum capacitances. Okay? Now, we realize these devices lithographically by adding, by patterning these types of structure. Then we embed this structure in a waveguide so that we can measure for up to very high frequencies. These are waveguides that are designed to guide frequencies up to some tens of gigahertz. we place this waveguide in a probe station that works at 10 Kelvin, and I will show you data only at 10 Kelvin today. And then we measure the admittance of the device, so the inverse of the impedance of the device, and I will show you what we observe.
Sorry.
Yeah?
Material? What is the TI?
Mercury telluride. So I've told you that there are two contributions to the capacitance. One is the quantum capacitance, one is this geometric capacitance. They come in series. On top of this, if you work at high frequencies, you have to take into account the fact that this is distributed. You have your electromagnetic wave that comes from this side that propagates in this device. And the best way to represent this is to have a 1D distributed model. And you can also take into account in this model the finite resistance of the TI film. An additional ingredient which is only there for experimental purposes but has no interest is the fact that there's an access resistance which takes into account the finite resistance between the contact and the material. Now if you measure that type of device, you can compute the admittance of this 1D line. This is something I'm sure you've done during your studies. And you get something of that kind, which is a complex admittance here, where J is the complex number usually written I. And this takes that form. This seems quite complex at the beginning, but you can actually see this in the following manner. If you look only at low frequency, what do you expect? You mostly expect the system to behave just like a plate-plate capacitor. And a plate-plate capacitor has an imaginary part which is omega times C. So this is what you see here. And the real part is basically 0. Now as you increase the frequency, you will be more and more sensitive to the losses in the film. And this is what you have here. You will have an RC time in the problem. And this is what you see here, where the losses go like omega squared. And this is just the usual RC squared expansion, where you have R times C squared times omega squared. And in this R, there's the access resistance, but here it's only an experimental issue. Now, as you increase the frequency even more, then you will really feel the distributed line capacitance with this distributed RC line. And at some point, you will see that the losses will start to win, and you will have evanescent waves propagating. And these evanescent waves, if you remember, for example, the skin effect in metals, you may remember that in that case, the admittance goes like real part equals imaginary part times square root of omega, or proportional to square root of omega. And this is something we observe at high frequency up to some correction given by the access resistance, which is, in that case, quite large. Okay? Here you see the data points in blue and red, and you see in black the fits given by the previous formula. So you see that the model works quite well, and that from this you can extract the capacitance. Now, as I told you, we want to study the samples. So what we measure is the capacitance for different values of the gate voltage. And we observe the following curve here. This is the capacitance function of the gate voltage, the total capacitance. And we see the following. First, we see a clear minimum here, which corresponds to the direct point where you would expect the density to be the lowest. And in that case, the quantum capacitance goes to 0. So this drives the total capacitance to go to 0 as well. And this is what we observe. Now, as you increase the gate voltage, you go towards the electron side, so you increase the electron density, and this increases the quantum capacitance. On the other side, you go to the hole side, you increase the hole density, and you increase the quantum capacitance. So this is reminiscent of this Dirac cone, except that you don't really read directly here the Dirac cone. And the reason is that this is the total capacitance, which takes into account the geometric and quantum capacitance. And I'm not sure I will have enough time to tell you in detail how we proceed, but believe me, if you drive the gate far away, the quantum capacitance goes to infinity because there are many, many states. So E squared times rho goes to infinity, just like the metal plate capacitor. And this means that the total capacitance will go to the geometric capacitance. And this is what we use here to extract the geometric capacitance around this value. Knowing this geometric capacitance, I will plot the quantum capacitance afterwards. Now, we have another type of sample which is slightly different. Here, the interface is mercury telluride to cadmium telluride, as previously. We also have other samples in which the mercury telluride is directly connected to some insulator, and there's no mercury cadmium telluride capping layer. And in that case, the interface is a bit different. There's a finite residual electron doping at 0 gate voltage, which you see as a shift of the direct point. And these are the two types of sample that we've tested. So I will focus on that sample. We'll try to show you the connection to these volkov-pankratov states that I've introduced previously, and I will come back to this sample at the end. So now that you know the geometric capacitance, you can extract the quantum capacitance and observe here this very nice direct cone feature. So of course, as you know from many models, in mercury telluride, the hole side is a lot flatter than the electron side, but you still see that there's this linear increase of the quantum capacitance, which is characteristic of direct bands. You can extract the Fermi velocity. It's in reasonable agreement with theory and experiments up to some error bars. But what is the most interesting part here is that you should look at this energy scale here. This energy scale here is huge. It's 300 millieV. It's about 10 times the transport gap that I've introduced before, which is on the order of 20 millieV. This means that not only in the quantum Hall response, but also in this compressibility response, you see a over a very, very large scale of energy, you see this Dirac-like response. And there's no sign whatsoever of the bulk bands. So this tends to confirm this paper here, which mentioned the fact that you could only understand the data if you would assume that the Dirac topological surface states would screen the electric field. And this tends to be confirmed here. Now the question is, what happens if you push the gate further? Does this break down at some point, and what do you learn from this breakdown? Now, if you push the gate even further, you see basically nothing in the capacitance. This continues to rise more or less as previously. But remember, I told you we can also extract the resistance of the layer. And if we look at the resistance, it has this peak near the Dirac point. It decreases as you increase the electron density, but at some point it starts to raise again here. And the best way to actually evidence this is not to look directly at the resistance, but to look at the diffusion constant. And in our system, since we can measure the quantum capacitance and the conductance, there's this Einstein-Boltzmann relation, which is nothing but fluctuation dissipation theorem that tells you how to extract directly the diffusion constant. And if you look at the diffusion constant, you see that plot here, which shows here this increase in the diffusion constant linearly with mu. And this is compatible with a high mobility, high constant mobility of about 120,000. The linear increase with mu is typical of screen charge impurity, but at some point you see that it breaks down. And this is typically around this 300 millieV, at which I pointed out that at some point we would see something happening. Okay? So here I've just tried to show you that up to 300 millieVs, which is a large energy scale, there's no sign whatsoever of any other states than the topological surface states. But as you try to increase even more the density, then you see that there's a decrease in the diffusion constant, which is a signature of a new scattering mechanism. And I will try to convince you now that this scattering mechanism comes from scattering through another state. So here at low energy, you cannot directly scatter. You have a high mobility because of the topological protection against backscattering. But at some point, you reach a high energy state, and this can mediate scattering from one side to the other of the surface state. I will show you some additional signature, and I will try to show you that we think this is the first sign of the volkov-pankratov excited state. So here I've shown you that there's a decrease in the diffusion constant. There's something else happening at this energy scale. There's the fact that at some point the gate starts to have some charge metastability. So you sweep back and forth the gate, and at some point you start to see that the gate starts to build hysteresis of that size. And this gate hysteresis is usually understood as the fact that you start to put some charge, not only in the states that you were initially gating, but in some other states. And usually in dirty semiconductor interfaces, these are just trap state at the interface between the insulator and the semiconductor, for example. But here this happens to be exactly at the state at which the surface state starts to have scattering. So these are states that are strongly connected to the surface states and not just some trap state way above the electron gas that you're looking at. This can be pushed to even larger excursions of the gate voltage, where you start to see that the hysteresis is getting bigger and bigger. And if you look at the way the metastability grows, you see that the onset of metastability is exactly where there's this new scattering channel appearing. There's something else. You can also do Magneto Transport in these devices. And you see also in the Magneto Transport that at low gate voltages, you have a linear slope. This is typical of single carrier transport. You have some Shubnikov-de Haas oscillations at larger field, but basically at zero field, this is linear. While at some point, at some gate voltage, you start to see this S shape here. So this is very shallow. You can plot the derivative and convince yourself that there's a real kink in the slope here. And this is typical of two carrier transport. You can fit this with this formula, which are widely used for two carrier transport. So somehow, this tells you that at some point, there's a second type of carrier that enters the problem, that they will play a role in transfer of charge between states because they are strongly connected to the surface states, so they introduce a new scattering channel. They also participate to certain charge metastability. Now, what is the connection? How strongly can you build the connection to the volkov-pankratov state? And this is where I will come back to this plot here that I've drawn here for realistic conditions, where you see here on this axis the electric field that we apply, and you can actually see that we reach something of the order of 5×10⁸ volt per meter. So this is quite large fields, and this is realized thanks to very thin gate insulators. And here you see the charging line. We can calculate from the quantum computation, from the capacitance, how much charge we move, and we can get the density from this. At zero electric field, zero gate voltage, we are almost at zero charge. And as we increase the electric field, we move along that line. And this is where, at some point, we start to see this metastability, this new second type of carrier in the quantum Hall response, and so on and so forth. And if you look at the numbers that you extract, you see that this is fairly close to the zero electric field response. That this would correspond to a breakdown field of the order of 5×10⁸ volt per meter, and more something that we understand of a coherence length of interface depth on the order of 5 nanometers. And 5 nanometers is really something realistic, because if you look at, for example, K.P calculations that calculate how thick the wave function is, you see that the wave function usually extends over some few nanometers. So this is 0 and this is 15 nanometers. So this is not unrealistic to think that these surface states correspond to a coherence length on the order of a few nanometers, and that this is actually the new the volkov-pankratov state I mentioned earlier. Now, to be more convinced, I told you we had a second type of samples for which there was a residual doping already at zero electric field, at zero gate voltage. What this means is that this point, corresponding to zero electric field, will already correspond to some given density, and that the Dirac point will be obtained for an electric field that is non-zero. So basically, this means that this charging line here will be shifted to another line here. And this is what is drawn here, where you see here the initial Dirac point, so the initial zero density, which corresponds to a finite electric field. And as you increase the density, this has to be a straight line, by the way, thanks to Gauss theorem. Then you will move along these lines, and you will see accidents for different electric fields that you can actually see already directly here in these oscillations of the diffusion constant, or equivalently of the conductance. So this is our first attempt at probing the screening in these topological insulators, and I hope I've convinced you that we see first hints of these excited volkov-pankratov states, that the numbers fit well with what we would expect. There's no fitting parameter whatsoever in this model, apart from the fact that it's a toy model. It's fairly realistic in terms of parameters. But obviously, as many of you think, there should be additional observations of these states. And we are hoping that, for example, some RPES observations in that direction will be done, and there are some works where they observe already tons of excited surface states in the RPES measurements that they can fit. So they involve here band bending in these arguments, but we wonder if in some paper there could be also just volkov-pankratov, because there's no intentional band bending. To conclude, because I think I'm basically done now. What I wanted to point out in this first lecture is the fact that the screening in topological insulators can be quite rich, and a source of new screening properties that will enrich our understanding of topological insulators, and that this calls for more experiments and also more theory. This anomalous gating response is typical of TIs, as I've shown you from the fact that there's this screening over large energies, that we can explain it with volkov-pankratov states, that we have first signatures in compressibility and also named this scattering spectroscopy. But there's some work to be done. First, we would be happy to see that in other systems, other 3D topological insulators, other systems just like 1D, this is not related to the 3D case. This could be happening in other dimensions also. And there's, for example, a theory paper from 2013 that points out the existence of excited states also in 1D, where the Majorana states have excited states also. Tineke, I know here in this room, is working on the case of 2D topological insulators. So if you're interested, just go to her poster. This also brings new ideas. How can you engineer these topological states to be, for example, more robust? What happens, for example, if you start with a huge initial doping that brings you to that region? This means that whatever you do on the charging line, you will never see anything that looks like a Dirac point. So is it pointless to look for Dirac points and Dirac physics in largely doped material? This is not something we can really answer to yet, because we don't understand what's happening on that side of the transition yet. This also tells you that you're dealing with real materials, and you should not look at these interfaces as being infinitely abrupt or whatever. You should really look at carefully at what you, at the way you model, for example, the insulating layers and the trivial insulator, what's the amplitude of its gap, and so on, and what's the quality of the interface, for example. And with this, I thank you for your attention.
It's not direct measurements, right? I mean, can you just try STM measurements?
I'd be happy if some STM people could actually see that. We are not STM people, so...
Yeah, but I mean, that's good, those are states, but you cannot do it while you're not...
We would be very happy. I think, so one important point still here is the fact that you need to apply some electric field, probably, to see them. Because at zero electric field, they might be at very high energies. And this is, in that sense, not very relevant for example, ARPS people which cannot apply any electric field. So they can create or not artificial bending, but they cannot really apply like a real electric field. So, for example, scanning gate people could observe these. And this is yes.
The state.
But yes.
You can reach the state via doping, or
yeah, there are other methods, but you need some tuning parameters, because very likely if you don't do anything, then they will be split at very high energies, and you may not see them. They mostly become relevant when you try to have field effect devices, which are relevant for huge amounts of devices. When you want to do spintronics or any semiconductor devices, you will need field effect. So it doesn't mean that it's irrelevant, but in some specific experiments, you may or may not see them.